folks, we're starting chapter 6. Chapter 6 is about counting. As we discussed in chapter 2, when we were talking about cardinality, the term countable refers to, like, doing a bijection with the natural numbers, right? 1, 2, 3, 4, like that. But when I say counting in this context, what I mean more is enumerating. And the idea of enumerating is figuring out how many elements are in a set. And we are going to be working specifically with finite sets right now. Finite sets. Okay, so we talked about that countable infinity and uncountable infinity. That's all fine, but let's just bring it back to, like, let's bring it back to something tangible. Talk about finite sets of things. But normally, like, so if you have a finite set of things, if you can look at it, you can count it directly, right? You can just be like 1, 2, 3, 4, 5. You can, like, count it out, right? But that's super slow. That's very inconvenient to actually, like, construct the set of things and count them. What's a better approach is to have some way of calculating the number of elements in a set without having to literally count them, right? So if you're thinking about from a computer programming perspective, if you want to count the number of different combinations of things, or the number of different possible configurations, or the number of different ways in which a certain process can be done, you don't want to have to do that by constructing all of the different cases and then enumerating them with a counter, like going maybe you have like an increment. You don't want to have to, like, actually, like, increment through a set and then count them. That's super inefficient. What's better is to come up with look at some rules about how many things there are going to be when you're counting different combinations, and then you can use those rules to basically just do, like, arithmetic to come up with the answer. Okay, multiplying things, raising things to powers, adding stuff together when necessary, that sort of thing. So that's what we're going to be studying, the more sophisticated approach to enumerating. So let's look at this first example. I talked about different combinations of things. This is a very simple example. We have 6 shirts, 5 pairs of pants, 2 jackets, and 1 pair of shoes. We are going to define an outfit as one of each of those things. Okay, so 1 shirt, 1 pair of pants. Let's assume you're wearing underwear as well. I didn't mention the underwear, but 1 shirt, 1 pair of pants, a jacket, one of the 2 jackets, and your pair of shoes. Okay, 4 things. How many different possible outfits are there, right? Well, we could list out all the different possible combinations and count them by hand, but that sounds like a super long and boring way to do it. Better, we can count the number of combinations using what we call the product rule. Okay, the number of ways to do A and B in either order is the number of ways to do A multiplied by the number of ways to do B. So just take the shirts and the pants, just those 2. The number of different combinations of shirts and pants is 6 times 5, 30, right? So because for each of the different shirts, you could pair that with each of the different pairs of pants. That's 6 times 5. Now, if I also have the jacket and the shoes, then I just multiply them all together. So the number here is 6 times 5 times 2 times 1. And we get 60 different outfits. And obviously that was much easier than listing out all the combinations and counting them a long way. Okay. So one way to think about this, the use of this product rule is like this. If you're kind of trying to count the number of different ways in which a procedure can be performed, you break the procedure down into a sequence of tasks, and then you count the number of different ways in which each task can be completed. So the procedure here is take task 1, choose a shirt. Task 2, choose a pair of pants. 3, choose a jacket. And 4, choose shoes. You're going to get an outfit if you perform those 4 tasks, right? And it doesn't matter what order you perform the tasks in. If you perform the tasks, if you renumber the tasks in a different order, still complete the same procedure, and it doesn't matter. So we don't have to consider the order in which the tasks are performed. Instead, we just have to consider the number of different ways that we can choose a shirt. There's 6 ways to do that, right? There's 5 ways to choose a pair of pants because we have 5 pairs of pants. We have 2 different ways that we can choose a jacket because there's 2 jackets. We only have 1 option for choosing shoes. Right? We only have 1 pair of shoes. So that's a way to think about it as a sequence of tasks. Okay. Questions on that one? Let's get the next one up. So the product rule deals with and, right? What about if you have or? Here's example 2. Oof, that's a bit. I think I might have compressed it a little too far. There. Let's. There we go. Okay, so suppose that 1 representative must be chosen from either students or faculty. Right, we're going to have like a representative at large for the college, right? Either a student or a faculty. If there are 63 students and 15 faculty, in how many different ways can the representative be chosen? Well, here we have an either or, XOR situation, right? So in the XOR case, we apply the sum rule. The number of ways to do A or B, but not both, so A XOR B, is the number of ways to do A plus the number of ways to do B. So in this case, we have students, we have faculty. We're assuming that there's no student who is also a faculty. So that's a little bit of an assumption. If you had like a faculty member who was also classified as a student because they were enrolled in a class or something, then that would kind of mess this up. But assuming that we have these 2 distinct groups of people, students and faculty, it's just going to be 63 plus 15. And we have 78 different possible ways to select a representative. So that's a nice, easy one right there. Okay. So now it gets a little more interesting than that when we start sort of combining these different rules. So here's the next one. Squeeze that right in there. I'm going to try to fit all these examples on this page. I'll probably have to move to a next page soon. So for these next few examples, we're going to deal with counting different types of strings. So I introduced strings before the quiz, right? So let's review that. A string is an ordered sequence of characters, finite in length. Usually, I said usually finite in length. You can hypothetically talk about infinite strings, but we rarely ever do. Okay. Repeated characters are totally fine. Sometimes there's specified otherwise. You can have like, oh, let's have a string, but with no repetitions, right? So occasionally we might specify that. That would be like an extra rule that we impose on the strings that we're counting. You can select your characters from any set of elements. An alphabet. It's called an alphabet. So, but it doesn't have to be like the alphabet that we use of the Arabic our alphabet is the Latin alphabet or whatever. It could be Arabic numerals, right? Or we could pick some other alphabet from a different language. Whatever, just any set of characters is a valid alphabet. And then we have this thing called the empty string, which is a unique string of length 0 denoted by the Greek letter lambda. This can get confusing if you happen to be using the Greek letter lambda as a character in your alphabet. Then you might want to pick a different symbol to represent the empty string. But as long as we're not using like Greek letters, then we'll just use lambda as our. So lambda, to be clear, is not a character. Lambda is a special symbol that represents a special string, which is the empty string. Okay. All right. So examples, letter strings, like A, B, C, A, X, Y. There's some examples of letter strings. I'm using capital letters here, but you can use capitals or lowercase or some combination. The empty string is a valid string. Digit strings, 0, 1, 2, 5, 9, 9, 8, 7. Again, the empty string is valid. Bit strings in particular use ones and zeros, right? Or empty. So let's do this counting problem. How many letter strings of length 4 start with A, or they start with BC? Okay, so first of all, let's identify how many letters are there. We're using our alphabet. We have 26 letters, right? So we've got 26 letters to pick from. And then we want to know, we want it to be length 4. So we can represent a string of length 4 with 4 blanks. This is how I like to do it. I like to draw it out. 4 blanks, blank, 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 blank. Right? And we want to know in how many, so it's how many different strings either start with A or they start with BC. So we can break this into 2 cases. Case 1, A blank, blank, blank. Case 2, BC blank, blank. Right? In case 1, we need to count the number of strings of this format. And one way of approaching this is to think about like constructing such a string. Okay, so how would we construct a string that starts with the letter A? And we want to think of all the different ways in which we could do that. And I'm trying to approach this, in this way I described over here, where we're thinking about this as a procedure, which is a sequence of tasks. And we want to count the number of different ways in which we can complete the whole procedure. So my procedure is to select the characters in the string. So the first character is A. There's no, that is fixed, so there's no other way to do that. That's not part of the procedure. But the second character, there's 26 different options for what that character could be. That's the first task in the procedure, is to select that character. Then we select the second character. There's also 26 options for what that could be. And then we do the third character, and there's 26 options for that. So what we get here is the number of ways to construct a string of length 4 that starts with A is 26 cubed. Okay, that counts, that enumerates the number of the strings that are that fall into case 1, right? Starting with A. And now for case 2, it starts with BC. We only have 2 more blanks. Each of those can be any one of 26 different possible characters. So we have 26 squared. So the answer is 26 cubed plus 26 squared. And the reason we're using plus right here is because this is case 1 XOR case 2. There's no overlap between the 2 cases, right? Either it starts with an A or it starts with a BC, and it can't be both, right? So there we go, 26 cubed plus 26 squared, and that's like, what is that? That's like 18,252. There we go. Okay. All right. Just a heads up, a lot of the answers to these problems are going to be very large numbers. That's fine. Okay. Sometimes in this unit, students will come up with a very, very large answer, and they'll say, oh, that can't possibly be right. When in fact it is right. Okay, so don't be alarmed by astronomically large numbers. Just for example, if you take a deck of playing cards, which is 52 cards, and you count the number of different ways that those cards can be ordered, the number of different orders, the number of different ways to order the deck of cards, right? It's 52 factorial. We'll get to that in a little bit. That number is bigger than the number of atoms in the known universe, I believe, if I'm not mistaken. It's like bigger than the number of seconds since the Big Bang. It's like ridiculous. Okay, so like, yeah, just so you know, there's some big numbers, and a lot of times instead of actually answering with like the number written out, we will just answer with a formula for the number and leave it at that. So like on this problem, if you encountered this problem on a quiz, I would accept 18,252, but I would also accept 26 cubed plus 26 squared. That's a formula for the answer. Okay. Okay. So next example. So now we are going to change this ever so slightly. It's very similar to the previous one. How many letter strings of length 4, again, start with A or end with BC? Now we have these cases. We have case 1, A blank blank blank, right? And as we said before, this is going to be 26 cubed different possible strings, right? Case 2, blank blank BC. 2 blanks, each of which can be any of 26 different letters. This is going to be 26 squared different possible strings. Okay. But this time there's overlap between these cases. So it is not case 1 XOR case 2, because it's possible to satisfy case 1 and case 2 at the same time. It's not like an XOR. Does that make sense? It's a or case 1 or case 2 or both. And the overlap is A blank BC. And since there's only one blank, there's only 26 different possible characters, different possible strings of that form, right? You just have one blank to fill, so 26 options for what you put there. So now, when there's overlap between cases, we apply this rule, which can be called the subtraction rule, or a more general version of this rule is called inclusion exclusion. Inclusion exclusion is a slightly more advanced counting strategy that basically works with like when you have different overlapping, like intersecting sets, which you're trying to count. It's a very useful counting strategy. So it's the number of ways to do A or B. So construct a string that looks like this or like this, but regular inclusive or, okay, is the number of ways to do A plus the number of ways to do B minus the number of ways to do A or B. So we can visualize this as here's A, here's B. I think I said an or a second ago where it was supposed to be an and. This is an and, A and B. Here's A and B, right? So you start by counting these things. You enumerate the number of ways, ways to do A, or in other words, like elements in the set A. You count those. That's, what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we have 10 things in A. Then you count the things that are in B. 1, 2, 3, 4, 5, 6, 7, 8, right? I've counted the purple ones twice. right? So the answer isn't 10 plus 8 because the purple ones in the middle have been counted exactly 2 times. So what I need to do is subtract exactly 1 copy of the number of things that are in both sets, right? Purple, 1, 2, 3, 4. And then having subtracted that intersection once, I go from having counted it twice to having counted it once. So it's basically a correction. So we have down to 14, right? And now we know the cardinality of A union B is 14. Okay. Actually, a way to say this, written out in terms of set notation, is that the cardinality of A union B is the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A and B. And this is this. They're the same thing written in different ways. Remember that union corresponds to or, intersection corresponds to and. So so these basically mean the same thing. Okay. So that is our subtraction rule. So that's what's happening in this example up here. We have the 26 cubed for A. We've got I'll use my colors again here. We've got the 26 squared for the strings end in BC. And then we want to subtract from that a single 26, which is the strings that lie in both sets, which we overcounted. We accidentally double counted them, right? Not accidentally, we intentionally double counted them. And now we are accommodating that double counting by correction. That's slightly smaller, 18,226. Okay. Here's another good one. So when you are applying the sum rule, right? When you're looking at A or B, like when you're looking at cases and you're adding up, you got to think about whether or not there's any overlap between those cases, because if there is, you need to also apply this subtraction rule to add them up, but then subtract the overlap. And when counting the overlap, you might need to use some other rule like the product rule when counting the overlap. Okay. Is this all going okay and making sense so far? Anybody have questions yet?
I got a quick one.
What's up, Ben?
So overlap, if you had A or C, then it'd be 26 times 26 would have been the overlap.
Sorry, what's the question?
So if I was just looking at your overlap, the middle line there in your example, let's say it was A or B, right? Or A or C, they had two characters unknown, that would be 26 times 26 for an overlap.
Yes, that's correct. If there were two characters, so like if instead of ending in 2 letters, if we had been ending in just 1 letter, then we would have had another blank here. And then this would have been 26 squared, but this also would have been 26 cubed. And then that would change the numbers. Does that make sense?
Yes.
Cool. The fact that the string has to be length 4 is one of the like restraining pieces of information here. So that's kind of what determines like how many lengths there are, right? So we always want to look at those constraints. Okay, so let's do some examples. All right, here we go. Here's 3 examples. How many bit strings? So now we're talking just zeros and ones, right? How many bit strings of length 5 contain a certain substring? A substring is a consecutive string that's found inside of a larger string, right? So for example, 0, 1, 1, 0, 1, it contains the substring 1, 1, 0, and you can see it in bold there, right? That's a substring. But if you look at 1, 0, 1, 1, 1, it does not contain that substring. You can't find the 1, 1, 0 substring anywhere in there. And this one, 1, 0, 1, 0, 1, does not either. So the substring has to be consecutive. So even though we have a 1, 1, 0 occurring in that order, it's not consecutive, right? There's this 0 that interrupts that pattern. So that does not count as containment of the 1, 1, 0 substring. Okay, this is I'm clarifying this point because there's also some instances where you're looking for occurrences of a pattern, but it doesn't matter if they're consecutive or not. For a substring, for that word, we need it to be consecutive. Okay. Make sense? So we want to know how many bit strings of length 5 contain this substring. How could we go about approaching this counting problem without just writing out all the different possible examples and hoping that we get them all? Thoughts?
My thought is that you write the 3 cases that you would find the string 1, 1, 0 in, because it can only be in 3 places, which is the beginning 3, and then the middle 3, and then the last 3. And then we know that there's only 2 possible numbers that could be placed in each place. So it's 2 plus 2 plus 2 plus 2 plus 2 plus 2, which equals 12 possible strings.
We add this 2 plus 2, 2 plus 2, 2 plus 2, and then we add all these.
Yes.
I think there's a formula to this. So something like for length n, subtract the length of your substring minus 1 is kind of where my mind's immediately jumping, and then you can multiply that against the number of operators.
We can do this with the rules, with the basic rules I've laid out for you so far. So we don't need to reach for any special formulas out there. This is not quite correct yet. So Connor has very nicely laid out 3 cases. So that is perfect. I like that. I think approaching it with these 3 possible cases is good. But then within each of these cases, the way that we count the number of different possible strings is not by addition. All right, so okay, so CJ in the chat suggests that we use the product rule instead, and I see Mike has got a hand up.
Yeah, I was gonna say the same thing.
Okay. Yeah, this is where you think about it like this. In order to construct a string, we need to select what bit goes here. I'll use the word bit because it's a 0 or a 1, right? And then we need to select what bit goes here. So there's 2 things we need to do. The first and the second. It's an and, right? That's product rule, right? So 1 or 0 here. There's 2 options, but then we do and 1 or 0 here. 2 times 2. And same for this and same for this. So the result here should actually be, it's still 12. But only because 2 times 2 is the same as 2 plus 2. So coincidence that it happens to be the same answer. Now, we just very casually used the sum rule. We should consider whether there might be any overlap between these 3 cases. Comments? Or thoughts on that?
Oh, wait, never mind.
What's up?
I thought I saw an overlap, but I was mistaken. I will keep looking.
There's multiple overlaps. The first one takes place in this case of the first line equaling 1 1 0. Well, it could be it'd be 1 1. Sorry, it's between the first and the third is where the overlap. Is there overlap?
I don't think there's overlap.
I don't. Can it have overlap? Is actually the issue I run into.
So I'm hearing Kyler trying to find an overlap, and I just heard Wesley say you don't think there's any overlap. Do you want to expand on that, Wesley? Why don't you think there's any?
Well, just how the 1s and 0s are placed, I don't think there's room for any overlap.
Can we very clearly explain why there can't be any?
Because it has to be in the 1 1 0 like order.
Mhm.
And I don't know how to say, like, you can't fit another one of the other cases in another case.
Okay, yeah. So you're totally correct, actually. So Wesley is right. There is no overlap, but let's turn on our proof brains a little bit and see if we can identify what is a really convincing argument for why there's no overlap. Micah, I see a hand raised.
Yeah, so I would say because the there are 3 digits provided to us that need to be found in a space with a total of 5 digits. The last digit of that 3 value string is 0 and the first is 1. There's no possible way, and because the second one is 1, so because it's not symmetrical as well, there's no way that you could possibly start the string that we're looking for once and then have space to type out the whole string again starting with 1.
Sure.
That's probably not as concise as you wanted it, but I don't know how to articulate it quite better than that without writing it down.
No
Gotcha.
other case fits in.
Mhm.
No one case fits in another.
That's true. Yeah. So you're both right, and it's just I think that we need a little bit more. I'm looking for a more concrete argument for like exactly what would go wrong. Like what is it that's specifically preventing us from having overlap here? We can. Okay. So looking at I'm going to approach it this way. Just look at the first 2 cases, right? This could be a 1. So these could be equal to each other. These are already equal to each other. This could be a 0, which would make those equal. And these could be whatever. These are both like we are free, so they could be the same. But right here, those are specifically not equal to each other, right? So we could say there's no overlap between case 1 and 2. specifically because the third character in the string is different necessarily in order to have the pattern. What character, if you compare strings 1 and 3, cases 1 and 3, what character is it that it makes them necessarily different?
The third character.
The third character again, because that's again a 1. If you compare cases 2 and 3, what character specifically needs to be different? Case 2 and 3, so I forgot to ever label these, but if we compare 2 and 3, yeah, CJ's got it in the chat. It's the fourth character. The third character is fine now, but the fourth characters are different in order to fit into our cases we laid out, right? So I think that's what I meant when I was saying, you know, what's a more concrete explanation of why there is no overlap? It's just like, really, it comes down to these characters. The third character in the string is not the same. And then and when you compare these, the fourth character is not the same, right? So that's just a simple explanation of why there's no overlap. That's one way you can approach this kind of thing. Okay. And I don't necessarily need you to give me like a thorough proof of why there's no overlap, but that's the kind of reasoning I want you to be going through in order when you're checking. Okay. Because you got to be able to effectively check for overlap. Right. Okay, let's move on to the next example here. So this one is similar to one of the ones we did earlier. How many bit strings of length 4 start or end with a 1? How are we going to approach this, folks? Cases. Let's draw out some cases.
Case 1 would have 4 possible outputs, and case 2 would be same if my logic holds.
Well, let's draw the cases first. What defines the cases before we start counting them?
Case 1 is a 1 in the first slot, 2 slots with either 1 or 0, and then the third slot being 0. Sorry, the fourth slot, not the third. I misspoke.
Sorry, what's the fourth? What's the fourth?
0.
0? Oh, okay. What's your case 2?
Case 2 will be the inverse. 0, like 1.
Okay. Are those the only cases?
Would there be a third case where it started with 1 and ended with 1?
And unless, are we saying that OR is inclusive? Where it starts or ends? I was arguing that it is not inclusive.
So remember, OR is always inclusive unless specified otherwise.
Okay.
Yeah, for the entirety of this class, I'm going to be consistent with that. Okay, if I say OR, it's inclusive OR. If I mean XOR, I'm going to say XOR. Okay. Or I'll write or, but not both, right? Either way, like I'm going to specify not both, if I mean not both. So yes, this is inclusive or. So Yasu is correct. We do need to make sure that we, oops, I labeled it case 2. We do need to make sure that we include this case as well. Is that all of the cases, or is there anything else? Is there a fourth case?
I think that should be it.
I agree. Yeah, so now we count. In each case, how many options do we have? I think you might have said this already. Somebody might have said this already.
Two.
Just 2? Just 2?
I think so, yeah. 0, 1.
So in each of these blanks, we have a 0 or a 1, right?
Right.
So that's two options for each blank. But then if we want to count the number of strings of this form, we need to fill 2 blanks, 2 options for the first one, 2 options for the second one. So we have 4, and I'm writing equals here because I'm just pay attention to the blue. This is 2 times 2 equals 4. You can, just the blue stuff here forms a little equation. I'm using the different color to count. So each of these is 2. Okay. And again, we get 4. So we get 4 and 4 and 4. Now, for these 3 cases, are these 3 cases, is there any overlap, or are they mutually exclusive? Like is there any overlap between our cases?
There cannot be any overlap.
There is not, right? So we are just going to go ahead and add all these together. This is sort of a vague 4 plus 4 plus 4, and we get our 12 again. Okay, so it happens to also equal 12. There's another approach to doing it this way. So this is a great one. The way that Kyler got us started here with the cases was made it so that there was no overlap. We could have also done cases where we had like 1 blank blank blank, a blank 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 1, and then an overlap case of 1 blank blank 1. This would be 2 cubed, 2 cubed, add those together, and then subtract the overlap of 2 squared. And the result here, 8 plus 8 minus 4 is also 12. So that's an alternate way to approach that using subtraction. Oh, I think it's actually what Trevor was saying in the chat. Is that what you were referring to, Trevor? Yes. Good. Great. So let's look at one more. Now we're moving on from the bit strings. Okay, let's do a different type of problem. We've got lots of different ways we can use counting, right? So we're going to use it in a bunch of different contexts. Bit strings, or any other type of strings, counting outfits, counting different combinations, counting how many ways you can choose things from a set. Here's one. How many positive integers less than 100 are odd or square? How can we approach this?
Cases would be the easiest way to do this. Again, set a case for all odd numbers in the region, and then get a case for all square numbers.
Oh, hang on. Can you say that again?
Oh, is my mic not picking up properly? Let me.
It was a little quiet. I just didn't quite hear you.
Yeah, I've been messing with my gain a bit. 3 cases, 1 odd, 1 square, and 1 odd and square.
Okay, so we're going to do odd case, square case, and odd and square case. So again, we'll be approaching this with our add together and then subtract, right? So add up A plus B minus overlap. Okay, that sound good? How many odds are there? How many squares are there? And how many odd squares are there? So this is our inclusion exclusion again, this guy. How do we count the number of odds less than 100?
So since, it's less than 100, so we're not including 100, but that still includes, since it's an even number, we can divide that by 2. Since there are always, like, if it's odd, then the next one is even, and then odd. So there's 50.
Yep, every other number is odd, so we'll say, so we can just divide by 2. Good. We got 50 odds. How many squares are less than 100? If we don't have some fancy technique, we can always just count them on our hands or something. Just
9, isn't there?
it should be 9. Yep. Yeah, we got 9 You got 9 squares less than 100. That's correct. You know, from 1 squared up to 9 squared, 10 squared is equal to 100, and then beyond that, it's bigger. So yeah, we only have 9. And then how many of those squares are odd? If you square an odd number, you get an odd number. If you square an even number, you get an even number. So 1 squared, 3 squared, 5 squared, 7 squared, and 9 squared. That's right. So 5. So there we go. So we have a total of 59 minus 5, or 54 is the answer. Okay, we have time for one more example before we stop. And then we'll have to pick up on permutations next time. Okay. So our last example on this page is how many letter strings of length 4 contain the letter X? Okay, let's explore this just enough to encounter the complexity, to appreciate the complexity. Well, we could have 1 X, or we could have 2 X's, 3 X's, or 4 X's, right? Because in a string, you can have repeats. So if it just needs to contain the letter X, there could be anything from 1 to 4 X's. We start looking at cases. We have 4 cases, 4 subcases within that first case, right? Within the second case, we need to think about all the different ways we can place 2 X's. We can go about this in some organized manner. Here's an organized way to go about it. There's 6 of those, but how can you be certain that you got them all? How many ways can you have 3 X's? And how many ways can you have 4 X's? Just 1, I guess. Okay. Now we want to go through and like figure out how many options there are for the blanks, and then like multiply and add up all the results. All right. To this, I say, bleh. That sounds like a terrible way to do it. For one thing, how do you know if you're going through and like figuring out all of the different like ways that you can construct a string with 2 X's in it? How do you know that you got all of them? What if you accidentally missed one, right? Or what if we accidentally, in the process of writing these all out, what if we accidentally wrote the same thing twice? It's very error prone. There's a much simpler and more elegant solution to this problem, which I'm going to let you think about and see if you can come up with it over the weekend. Oh, it's probably in the video, actually. So if you watch the video, it's probably already in there. I don't know. If you haven't watched the video yet, try to come up with it on your own before you do. And we'll talk about it briefly in class next week. So reminder, no class on Monday and Tuesday next week. We have a very long weekend. You guys have an extra long weekend. I have work stuff on Tuesday, so I won't see you guys until Wednesday. Kyler?
Does the employee work thing apply to all teachers, or is that just math department, or who's that for?
Oh no, it's all faculty. Are you wondering? Yeah, so like all your classes should have should be canceled for both Monday and Tuesday. President's Day and faculty development.
Just was checking. One of my professors is not the best about documentation, so I thought it'd be better to check.
Pretty sure you might want to double check with them if it's like an evening class. Maybe they're still planning on holding class because our faculty development is in the afternoon, or more actually most in the morning. So I would double check. Bye, everyone.
I completely forgot we had a long weekend.
Happy surprise then, perhaps.
Yeah.
Have a great